Good morning and welcome to a discussion on future device form factors by Bill Lin from Dell and Paul Kaler from HPE. Okay, if you look at today's storage device landscape, there's not one form factor that meets everybody's needs. Essentially, we see three different form factors. The first is a large form factor being a best dollar per gigabyte. That's currently serviced by the 3.5-inch HDDs out in the market. We see that as being the best dollar per gigabyte for the foreseeable future. This device form factor is large relatively. It's moderate performance. It's basically used for archive and cold data. And since it is a larger form factor, it mandates a larger chassis depth or a deeper amount of space to house that form factor. The second form factor we see that's prevalent in the industry today is a smaller form factor that's mainly for performance storage. This is the dominant form factor that is used in servers today. It's the 2.5-inch HDD and SSD form factor that we currently have. But we need something that can support multiple interfaces, SAS, SATA, NVMe, CXL in the future. It's a moderate capacity form factor. It's not as big as your big best dollar per gigabyte, but something relatively decent. The reduced size was originally driven by the fact that to get higher performance out of an HDD, we needed to make the HDD smaller. So we shrank down from a 3.5-inch to a 2.5-inch. And since the 2.5-inch is dominant in the industry, the SSDs naturally evolved into that 2.5-inch form factor. And that 2.5-inch form factor works well for our shorter depth chassis and modular systems. The third form factor that we see in the industry a lot is a smaller specialty form factor that's currently serviced by the M.2. This is a specialty form factor where larger form factors just physically do not fit. Its primary use cases is for boot media, for logging, and for edge devices where the larger primary form factors like the 2.5 just flat don't work. These form factor devices are lower power with good enough performance and capacity and pretty much a low cost entry point. So if you go look at what is needed in the industry, what are the architectural requirements for a family of devices that will last for the next 10 years? So the first thing we need for a family is a common connector definition, and this is based on SFF TA 1002. This supports multiple protocols, PCIe, NVMe, CXL, or Gen Z. It also supports 3 different link widths, by 4, by 8, and by 16. This allows us to scale performance among devices in the same form factor. This is also a high-performance connector, and we believe will support multiple generations of PCIe, at least through PCIe Gen 6. The device sizes enable multiple use cases and allow us to implement multiple chassis types. So these devices are optimized for both 1U and 2U chassis heights. They're optimized to maximize capacity while also meeting the chassis depth requirements. So we need a family of devices that fit in longer chassis and shorter chassis. We also can vary the device thickness to allow us to either maximize capacity or enable higher power devices. So to do this, one of the really important things in this family of devices is having a common connector registration point for all variants. So this will allow short devices to work in long slots. It will allow wide devices to work in multiple narrow slots. but this does require that the wider devices be asymmetric, which means the connector is skewed to one side of the device so that it will fit in the same connector backplane position. So our proposal is for a cohesive family of devices. Currently, most people know this as what we call E3 in the SFF vernacular. But this could include a half-height, three-quarter length device that is 1X. The dominant member of the family, we believe, will be a full-height, three-quarter length 1X device. This will be your dominant SSD form factor at 25 watts. But the family also allows for a full-height, three-quarter length 2X device, which we used to call E3 thick. We believe this is a good form factor for mid-range storage class memory implementations, the higher capacity NAND devices, and maybe mid-range accelerators or computational storage. Then we go to the full-length devices. This is for our storage chassis, the big storage arrays. So this would be a full-height, full-length device, 1X at 40 watts. So this is for the higher capacity NAND storage. We also support a full-height, full-length 2-inch device at 70 watts. And this could be used for higher class storage class memory implementations. It could be for accelerators, inference accelerators, or computational storage. So again, what I want to stress is by having a common connector and common registration point for each device, we can have an interoperable family of devices where a thin could fit in a thick slot, or a thick could fit into two thin slots. A short could fit into a long device with the appropriate carrier and adapter. So these all interoperate in the same physical mechanic set. This does require the use of a wraparound carrier, so that allows us to fit multiple devices into a common mechanic set. It also allows us to vary the look and feel of the devices per specific OEM. So I'm now going to turn this over to Paul Kaler from HPE, who will finish out the discussion.
Hey, thanks, Bill. And if you could, just move the slides forward for me. So I want to talk a little bit more about the connector placement, the commonality that Bill was talking about, and how that enables the interoperability between device types. So you can see on the right-hand side, the graphics here, we've shown a couple of different variations of the form factor, both on the connector edge, bandwidth capabilities, the by 16 and by 8 and by 4 that Bill mentioned earlier. And really, this just kind of show that you can see where the connector registration has to be aligned and how the form factor grows from that card edge. So you can imagine taking the device on the far right that's a half height form factor that's a by 4 connect interface. And of course, that can plug into a physically larger drive cage slot, something like a full height slot that's a by 8 or a by 16. Of course, it can go up in that direction. You can also take a full height by 4, which is the other device there on the far right, the full height version of that. And of course, that can plug into a full height slot that's either a by 4, a by 8, or by 16. Now, what's really interesting about this connector, though, is that that's not the only interoperability capability to go from a lower lane count up into a higher lane count. You can actually go the other direction as well. So if you were to take a look at the blue PCIe by 16 implementation we have shown there, where that's a by 16 E3 thin, it's a full height 1X device, that can actually plug into a by 4 backplane. So that connector is actually capable of plugging into a lower lane count drive bay. And that's really could be interesting for a customer who has a hot spare and maybe they don't have the correct device type to replace, but they need to get their system up and running quickly. And we don't expect them to leave it in that state because you're not going to be getting the full advantage of that device. But you can actually go in that opposite direction and plug in a by 16 device into a by 8 or a by 4. And then, as Bill had mentioned, kind of the ability for a thick device to also plug into a thin slot. Of course, you can't plug into one thin slot. It's got to go into two. But it is designed that way with the wraparound carrier that would go on these devices, that you would be able to plug in one thick device into the drive bays that are two narrow devices or thins, what we're calling 1X now. And so that enables kind of the ultimate flexibility there to leverage your mechanicals that you designed for this across many different backplane implementations. So you could have your pitch at a narrow thin or at a thick 2X pitch, and you can really plug your devices in whichever way is needed. And as Bill mentioned, the asymmetry that this requires, you can see here really clearly in the thin and the thicks. 1X and 2X devices, where you can see the form factor really grows away from the card edge. And you can see how that would give you room to put in a second PCB for high capacity capabilities for NAND, or for storage class memory where you might need lower density chips, might need more real estate to get to the capacity points we need. All right, so next slide. We want to talk a little bit about LED behaviors, right? So we want to make sure that the family of form factors have a similar LED placement, and that really kind of gives customers a good similar look and feel across the different form factor sizes, so that they don't have to kind of understand LEDs differently across the family. One thing we did notice was that there's some functionality that's missing that we kind of see customers have a really big interest for. And one of those is the ability to do a locate for a device in a data center through a management application, whether that device is failing or there's some other reason that you want to pull that device. Customers like to see an ability to have an LED indicate which device you want to have pulled. And so we're proposing that a blue bicolor blue amber LED be put in the same place where we currently have just an amber LED. And that blue functionality can be used for both locate and safe to remove, which will be really interesting for CXL devices, as some of those are not native hot plug like we have with NVMe today. So being able to locate to the tech in the data center that, hey, not only is this the right device to pull, but it's also now safe to remove any software eject mechanisms and other things have been done. So those are some of the improvements on the LED front that we want to do with this family of form factors. And then Bill, next slide. And then here we just wanted to go over a couple of the potential implementations. Again, we want to kind of stress that all the specs and the numbers that we're showing here are kind of the maximum that the spec allows, given kind of a reasonable amount of cooling and other things that are expected. But this does not indicate necessarily what a product would be. All right, there's going to be a wide range of products that we expect within this form factor capability. So for instance, if you look at the typical, the E3 short thin, which is, we think, going to be one of the more popular implementations, right? That can support an interface with up to a by 16, but that doesn't mean that every SSD that's going to come out in that form factor will support a by 16 interface. And same thing for the power. We expect that different class of products will come out that use different levels of power. And this is to kind of give a guideline on what we think is a reasonable amount of power and thermals to cool for that kind of given volumetric. And we also touch on a couple of the estimates on our NAND placements based on the different form factors that are shown here. I'm not going to run through each one of these, but this will give you a feeling for what are the dimensions for each of the form factors and how many NAND placements roughly can we fit. For some of the NAs, those are really touching on kind of different device use cases. So the short E3 short thick, for instance, maybe won't be needed for a high capacity NAND if we can hit enough NAND placements on the short thin. So we don't quite know yet if the market is going to have a need to drive a large NAND density requirement there, but otherwise we might have that used for storage class memory or accelerators, as Bill mentioned. So that kind of wraps up our discussion today with some use cases, and hope you guys learned something new and interesting today. And thanks for taking your time to check out our presentation. Hi, everyone. This is Paul Kaler from HPE.
And Bill Lynn from Dell.
Wanted to thank everybody for attending our session. I hope you learned something. We're moving into the Q&A section now, so if anybody has any questions, please put them into the Q&A. We are going to read through some of the questions and in the chat. We'll try and go back and forth between the chat and the Q&A tab. All right, so see one of the questions here, the first one, is this different than EDSFF? No, this is EDSFF. This is really just kind of fleshing out the E3 form factor that is the SFF TA 1008 spec. We are looking at making some changes to that specification in the next week or two, publishing a new draft spec. So these are just kind of a preview of some of the changes that we're looking at making to the E3 specification. Bill, I don't know if you have anything else you want to add to that.
No, that's pretty accurate.
All right, question 2, where do your company stand on the developing debate here this week regarding E1S thicknesses, 15 and 25 millimeter? So I'll speak for HPE and then Bill can chime in. So between those two thicknesses, actually, HPE does not see a use case really for E1S primarily. We're really focused on the E3 form factor. So I'd say it's kind of we don't really have an opinion one way or the other because we aren't planning on using either of those two thicknesses.
And from the Dell point of view, we agree with HPE. We do not see a use case for E1S except in maybe some very, very specialized or boutique applications. Our primary focus is the E3 3/4 length full height device.
All right, we'll take this next question here. Is this concept considering to be compatible with E1S or E1L? No, this is a very different form factor. Obviously E1L is a much longer form factor, so and it's a 1U focused height. These are really more focused at 2U. So you could put an E1S into an E3 drive bay, but not the other way around. We are working on getting more compatible between the E1S length and the E3. That's going to be one of the changes that we're going to be proposing into the new draft spec. So yeah, they definitely share the same connector and pinout, and we are working on some of these draft changes to be more compatibility between the E1 and the E3 so that you could leverage an E1 inside of an E3 volumetric, whether that's an SSD supplier leveraging their E1 designs and then being able to put that in an E3, or being able to actually take an E1 product and with a carrier adapter plug that into an E3 drive bay. Another question on, are these all in the EDSFF spec? So this is, again, we're going to be updating the E3 EDSFF spec with some of these changes that we talked about today. All right, we've got a question, Bill, on E1 devices have a 2C connector which can support a by 8 interface. Do we think that's sufficient for high performance required for coherent protocols?
From the Dell point of view, we don't. For storage class memories, we believe we will need a by 16. That's one of the reasons we're focused on the E3 because it does support by 4, by 8, and by 16. The E1 does not allow that. So yes, we believe for CXL and some of the storage class memories, we're going to need the higher performance and higher link widths.
Yeah, and HPE would agree with that as well, right? At this form factor, one of the things that I think we'll see in the future is that it won't only be used for NAND or storage class memory storage devices. It certainly opens up the opportunity to be used for multiple classes of devices, whether that's a future networking device or accelerators, GPUs. And so, yeah, we do think that having that ability to go to a by 16 gives a lot more legs to the form factor. And then kind of, our goal is that this would at least last for 10 years, if not longer. That the 2.5-inch form factor is almost 30 years old. So we'd love to be able to develop a new form factor that has that kind of legs underneath it that can continue to grow.
Another point on this is the E1 is really space constrained. So having the additional PCB area in an E3 is really valuable. And the fact that you can grow the power envelope of the devices, in our case, we're going up to 70 watts, but in E3, we may actually be able to grow it beyond the 70 watt limit. So having that headroom in both PCB space and power is really valuable.
A couple more questions about a new spec. I think we've kind of already addressed that. How is it different from Gen Z? It's not. This form factor could be used for Gen Z devices as well. Another question about an E1S by 8. We could maybe touch on that briefly. That's not within this family of form factors. The new cased versions of E1S that kind of enable it to get to a by 8. I'm not sure I totally follow that question. Bill, do you see that one about asking for how does it fit in? I mean, this is really the E3 form factor, so it's really just kind of a new some new additions to it. It still fits into that last chart. I would recommend if you want to look at power, speed, and LED functionality, kind of go look at that, the slide that we talked about, LED functionality, and then some of the power and speed that was listed on the last slide kind of goes through some of that. So the widths for this form factor are 7.5 millimeter. There's a question about, I think there may be a little confusion on E1 versus E3. So these form factors widths are 7.5 millimeter and 16.8. That's the 1X and the 2X thicknesses.
I think we just clarified the width.
Yeah. And then so flipping over to the chat, because it looks like there were some questions that got put into the chat as well. What is the option that hard disk drive would map to for the future? So this is a kind of from the ground up form factor built for solid state media and kind of optimized for the package sizes that we see. Kind of to Bill's earlier point, very early on in the slides where we were talking about how SSDs really adopted the hard drive form factors of the past. This form factor was instead designed from the ground up for solid state. So you could potentially shoehorn a hard drive into one of these form factors, but that's not really in the scope or our current plan.
The other point on this is if you look at SFFTA 1009, that's the document that defines the pinout of the connector that goes on the device. And currently, we do not have an option for SATA or SAS. So those are the dominant HDD interfaces. If an HDD were to go into this form factor, it would have to be a native NVMe device. And I know people are talking about that, but currently I do not see that on anybody's plans.
Yeah, and then there's we got another question, Bill, on would there be a common latch or common slot depth. So for the E3 form factor, it does not have a common latch. It's actually designed to be used with a wraparound carrier, which provides a little bit more of a better mechanical interface to the chassis. So, and that also allows you to customize it if you're an OEM and you have a specific ID that you're trying to meet or match with your existing product lines. That gives you the ability to do that with the wraparound carrier. There's a question about common slot depth. I think what you're getting at there is there are two different lengths. There's a short or a long. So there are two different depths that you can use for this, if that's what you were referring to.
So currently we have defined in the specification a 3/4 length device and a full length. The 3/4 length is 112.75 millimeters, and the full length is 142.5, I believe, millimeters. There's nothing that precludes us from adding another depth to the specs sometime in the future. And actually, this goes to the next question that was asked is, are there any larger thicknesses supported like a 3X? We currently define a 1X and a 2X, but again, nothing precludes us from defining a 3X. If we come up with a valid use case for that form factor, we could add that to the specification in a future version.
And then, yeah, there's maybe a question just kind of on the nomenclature of what, referring to the spec, right? So this, in the version 1.0 spec, this was E3, the nomenclature, and it was, a short and a thick, thin, and so there was a lot of nomenclature that was kind of used in the initial spec. As we saw some of this capability to really scale it up or down, one of the things that was not in the original E3 spec, the SFF TA 1008, was a half height. They were all kind of 2U focused, and so that's something that we saw. There's a scalability capability with this to say you can either scale down, or like Bill just said, you could scale up and you could support a 3X. And so it's really looking at the PCIe add-in card nomenclature of half height, full height, 3/4 length. We started looking at that may make more sense to be able to describe the different scalable modularity that this form factor enables. So that's why there's some change in terminology, but it's still all really based on the same original specification. It's going to be tweaked a little bit here, as I mentioned earlier, in the coming weeks with the new version 2 spec. But there is some nomenclature changes that we're making as well to try and better show the scalability of it. All right, and then there's, so it looks like there's a question about networking connectors fitting in the wide modules. So we haven't, that's not the current focus, so we haven't, I don't think we've done any analysis at HPE of, where either a 2X or a 3X would enable what type of different modules plugging in. Bill, have you guys?
Yes, at Dell, we've started looking at this. An RJ45 and an SFP will fit into a 2X device. And if you notice, the new dimensions of the 3/4 length are almost identical to the OCP3 NIC. So that's one of the things we're exploring is could we leverage this form factor for a front-facing OCP NIC device?
Yeah, and that's actually a perfect segue into the next question, Bill. You want to handle that one?
Yeah, so SFF 1002, which is the connector specification, supports a 4C+, and it adds more pins than a by 16. The use case for that is the OCP3 NIC, where those extra pins that sit down below the by 16 are the sideband signals for the NIC management. So that's one thing we're looking at is can we support a 4C+ in this form factor? And that's a topic that's under discussion in the SFF committee now.
Right, and that really leads to the next question of other use cases, and that's exactly what we're trying to do. And with this new revision that we're making is to make it more compatible with different types of use cases like NICs. Potentially it's very similar in size if you're familiar with the OCP3 NIC. And so it's looking at how we could potentially leverage those designs into a form factor like E3 that is front pluggable, and of course accelerators and other computational storage devices. So those are all kind of the use cases we're trying to accommodate for in the future by making some of these changes now early in the life of the E3 form factor. There's another question on LED indicators. So right now, what we're looking at is having some minimal LEDs on the device, and then you can, if you're in charge of the platform level, you can drive different, basically states. There's, if you guys are familiar with the SES states that are defined for all what are control a lot of the LEDs today. OEMs tend to have their own patterns that they like to have, and so that is capable to be able to drive a custom OEM LED through the existing two LEDs or the bicolor LED that we're planning to offer with the new draft spec. And I think we just hit our limit for our Q&A, so maybe wrap up, Bill, and then head us out.
Yeah, one thing I would like to add to that discussion is the LEDs that we are defining in the 1008 are pretty much focused around SSD use cases and storage class memory. If somebody comes up with a different use case for an accelerator or a GPU or a NIC or something, then we're open to redefining the LEDs for that particular use case.
Yeah, that's a great point.
So, yeah, I really appreciate everybody's time, and really thank you for joining our session.
Yeah, thanks everyone.